So I'd like to thank the organizers for giving me the opportunity to speak here. My name is Nir Bar-Gil from the Hebrew University. And I'd like to tell you about some of our work in the context of simulation and control of open quantum systems. And I'll start with a one-slide kind of intro into the system that we work with. So it's an experimental talk. We work with nitrogen vacancy defects in diamonds, so a localized atomic-like defect in a solid lattice. And the idea here is that it's a relatively useful and convenient quantum system or quantum platform to work with since, well, first of all, it's a solid-state system. We can hold it in our hand and have defects inside that are quantum. Specifically, the ground state of this defect, the electronic ground state of this defect, is a spin triplet, which has pretty good coherence times on the scale of a millisecond at room temperature. So we call it our quantum spin or our quantum system, and that's going to be the degree of freedom that I'll always be alluding to or referring to when I think about the quantumness. And maybe also importantly is the fact that this little atomic-like defect in the diamond can be addressed optically. Of course, the diamond itself is transparent. We can shine green light on this defect, and then it would emit red light that's somehow related to the quantum state or the spin state of this defect, which we can then read out even at room temperature. So this is the system that we work with. This is what we will be doing. I'll just flash that it's a very versatile system because of its ease of use or convenience. And one can use it also as a sensor for measuring many different things. One can actually build sort of an optical microscope that can then be translated to provide additional information, such as maybe most trivially magnetic information. And one can build magnetic microscopy systems that can address interesting questions in various fields. What I'd like to focus here is on the quantum system as a platform for simulating or trying to address various questions in open quantum systems. I'll start by describing some idea or work on characterizing noise or incoherent errors in our system. These usually in our system come from a surrounding bath of spins within the diamond crystal that are the source of noise, at least in our system usually. But then I'll move on to trying to see whether we can, instead of looking at this surrounding spin bath as a noise source, try to use it as a resource and cool it down or polarize it so that it's a pure or nearly pure quantum state. If I have time, I'll move on to describing an idea on how to do this more efficiently in the case where we have a dense ensemble of these qubits, of these quantum spins, and where many-body interactions are significant. Okay, so this idea of robust bath characterization or noise characterization is actually based on theory by Ram Uzdin, who's actually in this conference, but he was very cheerful about mentioning that he's going to skip my talk, so I can't point him out. But don't tell him I'm going to skip his talk too, so there you go. But anyway, it's a very nice theory about how one can, in a realistic scenario, in our case it's our NV centers in diamond, but this could be relevant for other quantum systems, quantum computing platforms, whatever. Usually you want to be able to characterize or address or separate out the incoherent effects from the coherent effects. And usually that comes about whenever you try to drive your system in some way, but your drive is imperfect or somehow has some additional coherent artifacts. So what Ram was suggesting is a scheme, a measurement protocol in which we will be insensitive to the coherent errors, but leave in or be sensitive to the incoherent ones. And just very briefly, maybe Ram will go into details later on, But the idea is that if we can apply whatever it is, the coherent evolution periodically, so repeatedly in a periodic way, one can then build a weighted sum of measurables at the end of each periodic application stroboscopically in such a way that it would cancel out to higher and higher orders the unitary evolution and retain the noise contribution. So that's the essence of the idea. Once we have, and this has already been kind of written out or derived by Ram, so once we have this series expansion, one can use it to single out the noise. In our experiments, what we were doing was looking at a very simple scenario where we have measuring sigma x fidelity. So it's a Ramsey experiment where during what's usually the free evolution time, we have some coherent evolution along with some noise contribution. In our experiments, we can actually have a control knob on the properties of the noise that we experience. I mentioned earlier that our major noise source in these experiments are the surrounding spins, the surrounding spin impurities within the diamond crystal. These usually create non-Markovian noise, as can be seen in this plot. We're actually plotting this. It's called normalized fluorescence, but it's actually proportional to the fidelity measure that I showed you earlier as a function of time. And the non-Markovianity of this spin bath, of this noise, is coming from the fact that the spin bath that surrounds our NV actually has significant memory, has a relatively long memory time. As the noise becomes more and more non-Markovian, the cancellation effect in Ram's theory is less precise. So this precise, the distinction between the unitary and the noise effects is due to the Markovianity of the noise. As the noise becomes more non-Markovian, it will also start to cancel out. So, question?
So, where do I see in the curve that one is Markovian and the other is not?
I didn't get to that yet.
Oh,
just a second. So in this, I just wanted to plot the actual measured data in these two scenarios. The Markovian scenario is actually activated in our experiment by turning on a weak laser pulse, which actually essentially optically pumps or creates a depolarizing channel to our spin in such a way that we see a faster decay, and this faster decay is Markovian versus the non-Markovian spin bath, and that is exhibited by the t-squared nature of the exponent here versus the regular exponent for the top plot. One can, yeah?
I could fit an exponent if it's second one too.
Go ahead. No, you can't actually. I mean, maybe you can, but I can't. This is actually more pronounced when looking at Ram's weighted sum measure. And here we plot this, I apologize for the typo, this is supposed to be this S2, this S2 weighted sum up to second order for corresponding to the Markovian and non-Markovian noises that we saw before. And one can see a relatively clear distinction between these two artifacts, between these two noise characteristics. And it's an example of how this approach can very clearly distinguish between these two processes. I'm sorry? So as I mentioned, this weighted sum series that Ram derived, one can take it up to whatever order you want. We stopped at 2. One can go further. As you go, of course, as you go higher in the order, you can cancel out the unitary evolution better and better if it's a larger action. Yep.
Those weights, those WKs, are engineered for a specific kind of coherent error or generic coherent error?
No, these are generic for coherent errors. As long as and one can show that it's relatively easy. The only thing that you have to take into account that this measurable is stroboscopic, so you have a periodic repetition of the exact same thing.
So
That's,
you need to know anything about the design.
that's right, it's random. And that's why if the noise is strongly non-Markovian, then this might not cancel, then it could cancel the noise to some extent as well. So it works very well for Markovian noise.
So what's special about those WKs? Like what's...
Nothing. These are just weights that you can easily derive if you want to take a stroboscopic application of some Hamiltonian evolution and then cancel it out. Okay, I'll continue. You can ask me later. So I just wanted to mention we're still working on more experiments as a function of, so these were done for a given week drive. As I mentioned earlier, one of the main advantages or main selling points, let's say, of this approach is that it makes you insensitive to the coherent errors. This was done with a specific week drive, and these are simulations of our experiment for different drive strengths. Okay, so let's say that we have some coherent evolution with different drive strengths, and this is plotting the measured evolution, the measured decay, and this is the extracted S2, and one can see that you indeed become much less sensitive to the change in the coherent evolution, to the coherent error, and only sensitive to the incoherent part. Any questions about this?
What do you actually do in the lab?
Yeah, so this is what we actually do in the lab. So it's what one can do. This is, for now, this is a single qubit or a single spin experiment. It could be extended, of course. But it's a single spin experiment where we measure the fidelity along X. So it's a Ramsey experiment, okay? In the usual free evolution time of a Ramsey experiment, we can apply any unitary control. In the lab, we apply it using microwave fields. And one can also apply, whether you apply it intentionally or not, one can also have a non-unitary decay or noise. In our system, this comes either from the intrinsic.
Where is the S2? Where is 2? Where is Rambus hidden in this picture?
Yeah, he's very small. Look, so these are the measured data. This is what we do in the lab. We do nothing else. We measure the pulse sequence that I showed you before as a function of time. Now, as long as this thing, whatever it is periodic, so we apply it for time t, 2t, 3t, 4t, and these are the t's that you see here. So now I can just take this temporal data, take time t with time 2t, with the weights from Rahm's taper, and extract this.
Thank you.
I'm glad I was able to answer at least one question properly. Other questions? Yes?
Yeah, I think you were just about to say that. What's the difference? I mean, the Lindblad, like the Lindblad term there, it changes between the Markovian and non-Markovian experiments?
Yeah, so this is, I'm not sure if I know what you are aiming at, but there are two ways to answer this. First of all, experimentally, the noise is different because in one case, in the non-Markovian case, it's the intrinsic noise that comes from the surrounding spin bath. We don't really control it in our experiment. And in the other experiment, we add another decay term in the Lindbladian, if you'd like, that comes from some other source. In our case, it's an optical pumping mechanism that we can turn on and we can control and creates a depolarizing channel for the spin. And it comes in as an additional term in the Lindbladian, which is Markovian in this case and non-Markovian here. Okay? Okay, so I was telling you now about how one can use some smart schemes. I'm not smart, but Ram is, to be able to characterize your system, your quantum system, your open quantum system, in a way that's sensitive and also robust against somehow uncontrolled coherent errors. But in our system, we sometimes like to see whether we can turn things around and utilize the spin bath, the noise source, to our advantage. And one way to do this is to try to polarize that noise source. This is something that many people are interested in. We've also been part of some consortia that were thinking about how to polarize this surrounding spin bath for actual applications, like making more sensitive MRI scans with a polarized contrast agent and so on. And in our more quantum sense, we want to see whether we can polarize that quantum bath to make it into a quantum resource. So how do we polarize such a spin bath? The easiest thing to do is to just look at our NV spins, our NV quantum spins that are purified or easily purified with just shining green light. So they are in their ground state, while the surrounding spin bath, in this case nitrogen spins, they're completely mixed. We don't have any control over them. But if we can create a flip-flop interaction between these two, so transfer polarization from the NVs to the Ns, and then repolarize the NVs and repeat, then we can actually transfer polarization or cool down the spin bath around us. In order to do that, we need to be able to address to address the bath spins. This we can do. I don't want to go into too much details here unless you ask me, but we do this by measuring the NV spins while driving the bath spins, and that allows us to identify resonances in the bath spins, to identify the resonant energies of the spins within the bath. Once we identify these resonant energies, we can drive them. We can actually coherently drive the spins in the bath. These are Rabi oscillations of these bath spins. Once we can drive them, we can actually apply well-known schemes from the field of NMR. Everything we do with spins is actually well-known in NMR. So this is the Hartmann-Hahn scheme, where we drive both of these spin species at the same drive strength, so at the same Rabi frequency, and that brings them into resonance in a rotating frame, which then allows the polarization transfer process to occur efficiently. Okay, so this is a well-known Hartmann-Hahn scheme, and indeed it does work. So one can actually plot the polarization, so it's very difficult to measure directly the bath spins, so we always measure the NVs. So we measure the polarization in the NVs as a function of time, and we can see that if we do not bring these two spin species into resonance, into the Hartmann-Hahn resonance, then the polarization of the NVs is maintained for a relatively long time. But when we do bring them into resonances by driving them together, we get a very fast polarization transfer from the NVs into the bath. This was also demonstrated in Fedor-Yelesco's group a few years ago, coupling not to the a nitrogen spin bath, but to a nuclear spin bath of the C13s. And this is a very nice experiment where they could actually measure the enhanced coherence time of the NVs due to the fact that the bath has been purified. So if you have the spin bath around you is not in a thermal state, but is actually pure, then it doesn't dephase your spins anymore, and you can see an increase of coherence time of T2 star as a function of polarization. Now, this type of polarization of the nuclear spin bath is relatively difficult to do because it requires a high magnetic field. What we were trying to do is to see whether one can do this completely differently. A high magnetic field and also driving of the nuclear spin bath. we wanted to see whether we can do this without any driving and take into, or actually utilize the level anti-crossings that occur naturally within our system as a function of a static magnetic field that we apply. So the NV has, at zero field, a splitting of almost 3 gigahertz in the ground state and 1.5 gigahertz in the excited state. And as we increase the magnetic field, the Zeeman shift basically just linearly changes the resonant energies of the plus and minus spin projections in such a way that around 500 Gauss we have a level anti-crossing at the excited state, and about 1,000 Gauss we get a level anti-crossing in the ground state. Once we reach these points, then automatically we get this type of Hartmann-Hahn resonance, because the resonant energy of our NV becomes negligible or similar to the nuclear spin bath that we have. This is work that is actually done by Tai and Pavel from my group, and also Tamara, who doesn't like her photos to be taken. Sorry? In which nuclear spin bath? C13s. Yeah. I mean, let me mention that we're not really clear about exactly what's happening. I'll show you what we see. We're still taking some more data on this, but we believe it's related to the C13s. And again, as was done in this experiment that I showed you from Fedor's group, we were measuring the coherence, or the dephasing time, the T2 star time as it's called in NMR, as a function of magnetic field. But we can also separate out and measure this dephasing time for the 0 to +1 spin qubit or the 0 to -1 spin qubit. We can measure those separately. And from such measurements, you know, we take this data, we fit it, and we extract the dephasing time. Here we plot already this T2 star time as a function of the magnetic field. And this is data that was taken on a diamond that was specifically purified. So it does not have, it has a very low concentration of C13s. We actually see that both +1 and -1 spin projections behave relatively the same, and we get some weird behavior around the ground state level anti-crossing, which we don't understand. But in the excited state level anti-crossing, we actually don't see any difference. On the other hand, on a regular diamond sample in which the nuclear spin bath is a dominant source of noise, of dephasing, we see a significant difference in the coherence time, in this dephasing time, between the +1 and -1 states. Surprisingly, we don't see this effect in the excited state level anti-crossing. So what we kind of understand from this, or deduce from this, is that this is related to the fact that the -1 has this level anti-crossing versus the +1. Although we're still taking some more data, we do not understand why we don't see a similar effect in the excited state. I just wanted to mention that earlier work that we've done was aimed at trying to control this polarization, this bath cooling, without having to resort to high fields or very specific fields. So actually something that would work at low field. And the idea, this was done by Jonathan, who was in my group, and his idea was to take the regular Hartmann-Hahn resonance idea, so bring these two spins into resonance and then let them transfer polarization from one to another, but then introduce in the middle a refocusing pulse, a strong pi pulse, as is usually done in standard kind of dynamical decoupling type schemes. And that could allow you to realize this Hartmann-Hahn resonance even in low fields and conditions in which noise would be significant and would reduce the efficiency of such a process. So I don't want to go into the details, and the colors are crazy for some reason. But I just want to flash to you the fact that by applying this periodic pulses within the Hartmann-Hahn, the regular Hartmann-Hahn or novel scheme, one creates, it's sort of like a floquet, so one creates these higher harmonics of the Hartmann-Hahn resonance, and as you go to the higher resonances in this expansion, they actually become less sensitive to noise. They become narrower and allow you to perform this polarization transfer efficiently, even if you have noise. And we've done a few, this is also in progress, we've also done some experiments comparing the regular Hartmann-Hahn or novel to this refocused novel, and one can see the Hartmann-Hahn resonances multiplied to higher frequencies in this refocused scheme. And this is a little bit complicated technically, so I don't want to go into all the details, but we're still trying to finish up these measurements to demonstrate them on several different NV configurations. So one can use different schemes and to then polarize the spin bath that you have using the NVs such that it would reduce the adverse noise effects coming from it and maybe even use it as a resource. But in many cases, for example, in this example that I flashed where one wants to use the NVs to polarize a bath of spins and then use it as a contrast agent in NMR, you don't want to have one NV coupled to the many spins in your bath, because your polarization transfer would be completely inefficient and the cooling would take forever. So you actually want to have many of those NVs and then transfer polarization from all of them into the bath. When you want to have many of them, you reach the regime, or you could reach a regime where these NVs are now close together. They're so dense that their coherent interactions are no longer negligible. So you now have to take into account, when thinking about these Hartmann-Hahn schemes or whatever schemes that I mentioned before, you have to take into account the non-negligible interactions between the spins. So this is work that was done by Kevin Ben-Atam and my group. And the idea was to try to see if we want to be able to adapt our protocols, this Hartmann-Hahn or the refocused novel or whatever I showed you, to the case of interacting spins, we need to be able to control well a system of interacting spins, right? So the way we usually control these, whatever system, single spins or multiple spins, is usually using some Hamiltonian engineering approach where we apply kind of a periodic or stroboscopic pulse sequence or Hamiltonian evolution, such that at the stroboscopic points of this periodic protocol, we get some desired average evolution. This is, of course, well known. If we have interacting spins, we want to be able to control this non-trivial interaction part of the Hamiltonian. And the non-trivial part of this Hamiltonian has all of these terms. This is kind of like the tensorial part of the interactions. Usually when we apply control pulses, we try to use standard pi pulses or whatever. And these are taken from a cubic symmetry group, which is a very useful approach in almost any dynamical decoupling or dynamical control or average Hamiltonian scheme that you encounter. However, if you look at the symmetry of the interaction terms in the Hamiltonian of this interacting spin system, then this basis of control pulses does not allow you to couple all of the different interaction terms. So you basically are limited by symmetry in terms of what you can create in your average Hamiltonian that you want. So if symmetry is problematic, go to the higher symmetry group, and that's what Kevin did. So by going up to an icosahedral symmetry group, one can still work with a finite basis of control pulses and still use all the standard machinery of linear programming to find the average Hamiltonian, the control protocols to create the average Hamiltonian that you want. But now, these allow you to create anything within the interacting spin system. So it removes the restriction, the symmetry restriction, and allows you to create any Hamiltonian. And one can then just play around with it and use it to demonstrate the fact, for example, that one can just recreate decouple the interactions to create a simple sigma z term. This is what people usually want to do when they want to create a sensor. You want to sense something that acts along sigma z, like an external field. So the standard cubic approach would give you a decoupling sequence that leaves the sigma z term, but suppressed by a factor of 3. While using the icosahedral approach, one can obtain something that's only a factor of 2 suppressed compared to the non-interacting system. Also, if you're not restricted by symmetry anymore, then one can use the icosahedral basis to create a protocol that results in an effective average Hamiltonian that is a sigma x, sigma y coupling. 5 minutes, excellent. Which you cannot do with the cubic group just because of symmetry. So it gives you a bigger playground to play with. And in the few minutes that I have left, I want to kind of go back to our spin bath coupling and to see whether one can use the fact that we now have full control over our interacting spin system to see whether we can now take such a dense ensemble of interacting spins and use it to efficiently purify a surrounding spin bath. The maybe best known approach for this, also of course taken from the field of NMR, is to use a decoupling sequence where you have like this dense ensemble of spins. You decouple them. There's a well-known sequence called Wahuha that does this. There are also variations on it that are a little bit better. And then once you decouple the interactions, one can, at least in principle, try to use the standard Hartmann-Hahn or something like that, interlace these two together to transfer polarization. So what we've shown is that one can improve this by using icosahedral control and then decouple plus optimize the polarization transfer. One can look at how the polarization transfers as a function of time under different control sequences. The gold standard here is in gold. So it's the polarization transfer if you had a dense ensemble of spins, but there are no interactions. This is all simulations. These are not, we haven't been able to measure that yet. And this is then compared to the standard Wahuha here in blue, and then the sequences that Kevin came up with. And eventually, if you combine the coherent evolution that I showed you in the previous slide with repeated optical pumping cycles, so one can transfer polarization, initialize the NVs again, and repeat, one can actually calculate the polarization buildup within the bath and the speed of polarization buildup and the saturation. And one can see that the optimized sequences strongly outperform the regular Wahuha, both in terms of polarization transfer speed, but also in terms of avoiding various types of dark states that appear in the evolution and therefore allow for full polarization to occur. So with this, I'd like to close, summarize. I hope I convinced you that NVs are really cool and we can do many things with them. And I'd like to thank the people who've actually done the work, our collaborators, especially Ram, who's not here, funding, and you for listening. Thanks a lot.